Hello everyone. In this video, we learn of another approach to doing a hypothesis test. It's called the p-value approach, and it's very closely related to the rejection region approach. So what is a p-value? P-value is the probability of obtaining a number, the probability of finding a number that is more extreme than the specific test statistic that you're getting. So this may still seem a little bit abstract, so let me show you an example. So let's take the case of a right tail test, okay? Where the null hypothesis is mu is equal to mu naught, and the alternative is that mu is greater than mu naught. Now we'll go ahead and compute the test statistic, and test statistic is given to us as p star. Okay? Now the p-value by definition is the probability of the sample data producing either p star or a value greater than p star, or a much more extreme value. Now, when you actually look at our t distribution, right? If suppose p star is here, and if we are having a null of mu equals mu naught and an alternative that mu is greater than mu naught, okay? We know that we're going to be focused on the right tail of our distribution. And therefore, if our focus is on the right tail, and if we are interested in getting a value of probability that is greater than or equal to p star. So p-value essentially boils down to finding the probability of getting a number that is greater than or equal to p star, because something more extreme than p star would only be in this particular region. We're only focusing on the right tail, because mu is greater than mu naught. That's our alternative hypothesis. So some number more extreme than p star would mean something to the right of p star. And therefore, the probability of finding a number greater than p star boils down to this shaded region that you see here. And this shaded region is called the p-value, and it is written down as probability of p greater than p star. Now, intuitively, remember that we defined our rejection region to be P alpha, correct? Okay. So if this place were indeed P alpha, and that's my area. Now, if I look at the rejection region approach, my T star falls in the rejection region, and therefore I must reject my null hypothesis. Another way to think of this is that my p-value is lesser than or equal to my alpha. That is, this shaded region that you see here in yellow is only a fraction of this green region, right? And the green region is my rejection region defined by alpha is equal to 5%. Alpha could be anything, it could be 5 or 1% or whatever. And if I find a test statistic that falls in the rejection region, I must reject it. An equivalent way is to say that if the p-value for a specific test statistic is lesser than the probability that I ascribe to the threshold region, which is alpha, then I will go ahead and reject the null. On the other hand, suppose I get a t star that is here. If that is my t statistic, then my p-value will be this entire region. And in that case, we can clearly see that my test statistic falls outside the rejection region, which is this area. So when a t statistic falls outside the rejection region, we don't reject the null hypothesis. Similarly, if p-value is greater than alpha, do not reject null. This is all the p-value approach is about. And this is how it is equivalent to your rejection region approach. So this, I showed you the example for the left tail test. Sorry, the right tail test. Let's look at the left tail test. Okay. Oops. So we define our test statistic in a specific way. And we want to find the p-value such that we want to get what's the probability of finding a more extreme value than the test statistic. Well, if our alternative hypothesis is given by mu being lesser than mu naught, then we know that we're going to be focused on the left tail. Okay. And suppose I get a t star. Suppose I'm here and if I get a T star like this, and if my focus is on region to the left of the center, the probability p-value essentially becomes the probability of finding a value which is more extreme than T star. More extreme means beyond T star, and I look beyond T star in the left direction. And therefore, I'll be interested in computing this area. And that area where I'm trying to find the probability of T being lesser than or equal to T star, this becomes my p-value. So the p-value is essentially likelihood of finding a more extreme value than your test statistic. And depending on whether you're in a right tail test or a left tail test, you decide to look at the area to the right of the test statistic or to the left of the test statistic. So this is my P star value. Same logic as before, which we used for the rejection region approach. So if my minus P alpha happens to be here, okay, then clearly my test statistic is falling in the rejection region, and I'm going to reject the null. Another way of writing that using the p-value approach is to say that reject the null if p-value is lesser than alpha. If the area which is to the left of your test statistic is lesser than the threshold region that you're setting, then it means that essentially your t statistic is falling in the rejection region, and therefore we go ahead and reject them. If our p-value happens to be greater than the test statistics, suppose p-value is greater than our rejection region, suppose you get P star there, and if this becomes your p-value, do not reject the null if p-value is greater than alpha. So that's how you would interpret the p-value version of hypothesis test for a left tail test. Now, we look at a two-tail test and how to compute the p-values there. Now, for a two-tail test, we know that we'll have the center, and we're going to have our rejection regions on both sides of the distribution, on both tails. Now, the way we'll define p-value is that we're going to, this one is a little bit tricky, so pay attention to that. Now, we want to find the likelihood of finding a more, what's the probability that you'll get a more extreme value than T star. In the case of a two-tail test, a more extreme value needs to be interpreted as if you're looking at, you have to look at both tails to figure out the extreme values. And what do I mean by this? So suppose you get a T star that is, say, here. Okay? If that's the T star you end up finding, traditionally, if it were a right tail test only, I look at this area. Okay? And this is where probability of this is T being greater than T star. But now remember that I'm looking at a two-tail test, therefore I'm going to have rejection regions on both sides. I don't know what my alternative is telling me, that it could go either way, it could go to the right or to the left. Therefore, when I compute p-values also, I'm going to be looking at values that are more extreme on both sides of the tail. And how will I do that? Suppose my T star happens to be this number. I'll compute the area above that number. I mean, this number T star is to the right of my center, and therefore I look at the area to the right of T star. What I'll also do is, by principle of symmetry, I look at minus T star on the other tail, and I'll also compute this area. And this area is probability of T being lesser than minus T star. Okay. I look at both of these areas, and I'll say that my p-value, my sincere apologies for that. Oops. Nothing what just happened. I've been able to fix that. So this is nothing but P of T being lesser than minus P star. So my p-value essentially will be both of these areas. So p-value is given by P of t being lesser than minus t star plus P of t being greater than t star. In other words, p value is 2 times the probability of t being greater than the absolute value of t star. So whenever you're computing a two-tailed hypothesis test, look for probability values on either sides and add them up. Look for finding the likelihood of finding a more extreme value than t star on both sides, add it up, that's your p value. And naturally, the idea is to reject H naught if p value is lesser than, if p value is lesser than alpha. And here again, it flows from the same argument, right? If this is my alpha threshold, if this is p alpha by 2, and if this is minus p alpha by 2, naturally, in this particular example, our p value, when you add up those areas, it is lesser than the area encompassed in green. Therefore, our t star is certainly in the rejection region, and we go ahead and reject the null hypothesis. So the approach is that whenever we use the p-value approach, if p-value is lesser than alpha, you reject the null. If p-value is greater than alpha, you do not reject the null. Okay? So if this is alpha, and if your p-value is somewhere here, you reject the null. If this is alpha, and if your p-value turns out to be like this, you reject the null. And this is alpha by 2, and this is alpha by 2. If your p-value happens to be lesser than this, you reject the null. And then you state an overall conclusion, which is very similar to how we did it earlier. Now, I mentioned in the previous video that there's a very close link between the hypothesis testing process and constructing confidence intervals. The link is that suppose you decide to reject the null that mu is equal to some level at a 5% confidence or 1 minus alpha percent confidence interval, then the equivalent, if you decide to reject the null when at alpha is equal to 5%, the equivalent scenario is that the 95% confidence interval for x bar will not include that hypothesized mu value. That is, if you reject that the null is, if you reject your null hypothesis, your confidence interval will not include that hypothesized value. Or rather, another way to reject the null is you check your confidence interval, and if you see that your confidence interval does not include the hypothesized value, go ahead and reject the null. That's because all values in the confidence interval are plausible values of your population parameter, whereas values outside the interval are rejected as plausible values for the parameter. So if 95% of the time your mu is likely to be in that interval, only for 5% of the time the mu will be outside of that interval. And whenever you don't find the mu falling, you don't find your hypothesized mu value falling in that interval, you know that 95% of the time you don't observe that value, and therefore that is proof to rejecting that hypothesis. So for example, if you have a 95% confidence interval for x bar being given as, going from 2 to 11.26, and if I have a null hypothesis equal to, that tells me mu is 0, 0 is not in this interval. 0 is lesser than 2. Therefore, it is not in this interval, so I'll go ahead and reject the null hypothesis. So this is how your 95% interval and alpha is equal to 5%, those tests are related. Similarly, when you have a 99% interval and alpha is equal to 1%, that relationship is also similar. And if you're interested, I'll walk you through the math here. I'll probably put that down as a note for you to review. But there's a very close link between hypothesis testing and confidence intervals. So with this video, I think now you'll have a very good handle on how hypothesis tests are done. In the next video, I'll walk you through a few examples of two-tailed as well as one-tailed hypotheses. And we'll use Excel to answer these questions. And that way you'll get a flavor for using tools along with problem solving. So I'll see you in that video.